Another important physical property is ionization enthalpy. The energy required to remove the most loosely bound electron from an isolated gaseous atom, X, in its ground state is called ionization enthalpy. Ionization enthalpy is expressed in the units of kilojoules per mole. Energy is always required to remove electrons from an atom, and hence ionization enthalpies are always positive. The energy required to remove the most loosely bound electron is called the first ionization enthalpy. The energy required to remove the second and the third electron is termed as the second ionization enthalpy and the third ionization enthalpy respectively. The second ionization enthalpy will always be higher than the first ionization enthalpy. This is because, on removing an electron, the unipositive ion formed will have more effective nuclear charge. Due to this, the nuclear attraction on the electrons increases, and hence, more energy is required to remove an electron from the unipositive ion. The term ionization enthalpy, if not specified, is taken for the first ionization enthalpy. The graph shown here depicts the variation in first ionization enthalpies delta IH of the first 60 elements in the periodic table. As you can see from the graph, noble gases with stable Ns2-Np6 configuration have the maximum first ionization enthalpies and hence are chemically inert. The alkali metals, with one electron in their valence shell, on the other hand, have the lowest first ionization enthalpies and hence are highly reactive. The ionization enthalpy generally increases across a period because of the decrease in atomic size. In general, as we move from left to right in a period, successive electrons are added to the same shell. As a result of this, the nuclear charge increases while the shielding effect remains almost the same. Thus, across a period, the increasing nuclear charge outweighs the shielding effect. As a consequence, the outermost electrons are held more tightly, resulting in the decrease in size, and thus increase in ionization enthalpy across the period. However, there are a couple of exceptions to this guideline. To illustrate this, let's consider the first ionization enthalpies of the second period. The first ionization enthalpy of boron is slightly less than that of beryllium, even though the former has a greater nuclear charge. This happens because in the case of beryllium, the 2s orbital is completely filled and moreover, the electrons are present in the more penetrating s orbital. On the other hand, in boron, the outermost electron is unpaired and is also present in the less penetrating p orbital. Hence, more energy is required to remove a 2s electron from beryllium than to remove a 2p electron from boron. The other anomaly is the smaller first ionization enthalpy of oxygen as compared to nitrogen. In the case of nitrogen, the 3 2p electrons reside in different atomic orbitals in accordance with the Hund's rule. The half-filled orbitals confer extra stability to the nitrogen atom. However, in the oxygen atom, 2 of the 4 2p electrons occupy the same 2p orbital. This results in increased electron-electron repulsion. Hence, it requires less energy to remove the fourth 2p electron from oxygen than to remove one of the 2p electron from the stable half-filled nitrogen atom. Let's now discuss the variation of ionization enthalpy down the group. As we go down a group, although the nuclear charge increases, the size of an atom and the shielding effect also increases with the increase in the number of shells. Due to this, the nuclear attraction on the outermost electron is decreased. Thus, removing such an electron requires less energy, and hence, ionization energy decreases down a group. Let's look at yet another important physical property: electron gain enthalpy. It is the measure of the ease with which an atom can gain an electron and form an anion. The enthalpy change during the process of addition of an electron to a neutral gaseous atom to convert it into a negative ion is defined as the electron gain enthalpy. The process of adding an electron can be either endothermic, that is, energy absorbing, or exothermic, that is, energy releasing. It is exothermic when an element reaches a more stable state by the addition of an electron. For example, halogens attain a stable noble gas electronic configuration after gaining an electron. Hence, they have very high negative electron gain enthalpy values. On the other hand, noble gas elements have large positive electron gain enthalpies. This is because, in the case of noble gases, the electron has to enter the next higher principal quantum level, leading to a very unstable electronic configuration. Therefore, noble gases need to absorb energy in order to gain an additional electron. The variation in electron gain enthalpy of elements in the periodic table is not as systematic as the ionization enthalpies. Generally, electron gain enthalpy becomes more negative with each successive element across a period. In other words, electron affinity increases across a period. This is because, as we move from left to right across a period, the effective nuclear charge increases and the atomic size decreases. The addition of a new electron would be easier for a smaller atom because the added electron would be closer to the positively charged nucleus. The electron gain enthalpy decreases down a group because of increase in the size of the atom, and also the added electron would be further away from the nucleus. However, there are exceptions to this rule. For example, the electron gain enthalpy of oxygen is less negative than that of the succeeding element sulfur. And the electron gain enthalpy of fluorine is less negative than that of the succeeding element chlorine. This is because oxygen and fluorine atoms are smaller in size and have strong inter-electronic repulsions. During the addition of an electron to these atoms, the electronic repulsions are overcome at the expense of some liberated energy, and hence, the overall energy liberated is less in these atoms. However, For the subsequent elements, sulfur and chlorine, the electron gets added to n is equal to 3 quantum level. At this quantum level, there is larger space available, which reduces the electron-electron repulsion, thereby making the addition of a new electron easier. Another physical property of elements in the periodic table, usually confused with electron gain enthalpy, is electronegativity. It is the ability of an atom in a chemical compound to attract shared pair of electrons towards itself. It differs from ionization enthalpy and electron gain enthalpy, as it is the property of the atom in the bonded state and not in the isolated gaseous state. Electronegativity is a qualitative term that was devised by L. Pauling for better understanding of covalent bonds and their polarity. Although electronegativity is a qualitative measure, different scales have been developed to measure it, such as Pauling scale, Mulliken-Jaffe scale, and Aldred-Rochow scale. Of these scales, the Pauling scale, named after its discoverer Linus Pauling, is the most widely used scale to measure electronegativity. Pauling assigned an arbitrary value of 4.0 to fluorine. The table shows the approximate value for the electronegativity of few elements based on the Pauling scale. The higher the difference in the electronegativity of two bonded atoms, the more is the probability of the bonding electron pair to localize around the more electronegative atom. For example, in the case of water, oxygen being more electronegative pulls the shared pair of electrons closer to itself. As a result, the hydrogen atoms in water are slightly electron deficient, whereas the oxygen is electron-rich, causing an overall dipole moment in water. Electronegativity increases across a period. The increase in electronegativity across a period is due to the increase in effective nuclear charge. Smaller atoms have high electronegativity values than the bigger atoms. The larger the size of the atom, the lesser the tendency to attract the shared pair of electrons. This is why electronegativity decreases down a group. As shown here for the group 1 elements. The noble gas elements have zero electronegativity due to the stable octet configuration in their outer shells. Non-metallic elements have stronger tendency to gain electrons. Thus, electronegativity increases with the increasing non-metallic nature of elements across a period. As the elements down a group exhibit increasing metallic nature, the electronegativity also decreases.